Hi everyone, in this video I'm working through question 14 part E of the extension to 2020 Barker College assessment task number 2. So we're told to consider a regular n-sided polygon drawn around the outside of a circle of radius r and center O, such that each side is tangent to the circle at its midpoint, as shown in this diagram here. So the question has two parts. Part 1 says to show that the area of the triangle AOC is r squared tan pi on n. And then part 2 says hence evaluate the limit as n goes to infinity of n tan pi on n, giving justification for your working. So what I might do is I might work through both of these parts in this video, simply because for part 2 it follows on quite naturally from part 1 and there's not a huge amount of extra work to do, so it makes sense just to work through them both together. So yeah, let's take a look. So I've recreated the essential parts of this diagram. We're focused here on triangle AOC. This line AC is meant to be tangential to the circle, so yeah, just don't worry about that little gap there. It's meant to be a perfect tangent. Part 1 wants us to show that the area of triangle AOC is r squared tan pi on n. Now, I think whilst we're dealing with triangle AOC in its entirety, I actually think it's helpful to break up this triangle into two triangles, AOB and BOC. And I might actually just draw them up separately just to make it a bit easier to deal with. So let's just draw them here. So in terms of making sure I get these vertices correct, so it'll be O at the bottom here of both of these triangles, and it'll be B here, because we've got OB in common with both triangles, and they both have a length of R, being the radius of the circle. And so we'll have A over here and C over here, and they're both right-angled triangles. Now we're told that the tangent, this polygon, each side will be tangential to the circle at its midpoint. So we know that AB and BC will be equal. So we've already got OB as being the same. These two sides are identical, we know that. And we know these two sides are equal because we're told that B is the midpoint of AC. And so it wouldn't take a lot of effort to prove that AO and CO must also be equal. You just use Pythagoras' theorem if you wanted to work through the whole proof. But I think in the context of a 4-unit trial exam, just noting this on the diagram is probably enough. It's not the essence of the question, so I think, you know, I don't think you'd be losing any marks by not going through the steps of that proof. But what we can see is we're dealing with congruent triangles here, and particularly given AO and CO are the same, we know it's an isosceles triangle, so that these angles will be the same, angle OAB and angle OCB, and given they're right-angled, we know that this final angle will also be the same. So in other words, this line BO kind of cuts this total angle AOC in two because they're identical. And so I think it's helpful just to picture those two triangles and kind of just make really clear that they are congruent, and therefore there's some conclusions we can draw, particularly about these angles. But I think it's also worth noting that since these two triangles are congruent, since triangle ABO is congruent to triangle OBC, so we got ABO and OBC, what we can conclude is that the area of triangle AOC, the area of this whole triangle AOC, is simply 2 times the area of either of these triangles. So I'm just going to pick triangle ABO. So we can just focus on one of the triangles, work out what its area would be, and then double it to get the area that we really care about. So again, that's why it's helpful to break up these triangles. Now, in terms of angle AOC, this total angle, it's also worth noting that angle AOC would be equal to, well, in terms of going the full revolution around, that would be 2 pi. But because we've got an n-sided regular polygon, we know that all of these, I guess all of the triangles formed by the lines drawn around the outside of the circle, all of those triangles will have the same interior angle because the interior angles of a regular polygon are all equal. So if we've got an n-sided polygon, there's going to be n of these triangles, and so we can divide that 2 pi by n to get the total angle of any individual triangle that gets formed. So we can say that maybe the reason for that is that the interior angles of a regular polygon are equal. So from there, angle AOC is 2 pi on n, but we're actually concerned just with essentially half of it, since we know that these two angles are equal. Therefore, this line OB cuts that total angle in half. So we can say, therefore, angle, if we're thinking of the angle we really care about in this triangle, AOB, that's going to equal half of this 2 pi on n. So these 2's will cancel, so it's really just going to be pi on n. And that's a good sign, because pi on n is the angle that is sitting there in our result that we're being asked to show. So, so far so good. But now we need to think, well, what is this area of triangle ABO? How can we think about that? And I think we can just go back to basic half times base times height. So maybe if I kind of just restate this down here, we can say that the area of triangle AOC is equal to 2 times the area of triangle ABO, and the area of triangle ABO will be half times the base, which I guess we can just call AB the base in this case, times the height, which would be BO, which in our case we know is the radius of the circle R. So these twos, the 2.5 will cancel, so that the area, this total area that we care about, is just going to be the length of AB times the radius. And so now we just got to think, well, what's the length of AB? And given we see a tan of an angle here, it makes sense to think about what is the tan of, well, if the angle is pi on n, and we've just worked out that angle AOB is pi on n, it makes sense to make a note that the tan of angle AOB, in terms of this right angled triangle, it would be opposite over adjacent, so it would be AB divided by the adjacent, which is R. And so what we could say is that AB, that side AB, if we just bring the R up, will be R times tan of angle AOB. Now at this point I might turn over, but what we can say is therefore AB, the length of AB, is equal to R times the tan of angle AOB, which we've already worked out is pi on n. So we can say pi on n. So let's move this ruler. So putting all that together, we can say therefore the area of triangle AOC, the area of triangle AOC will be equal to AB times R. AB we just worked out was R tan pi on n times R, and these R's can just come together to be R squared tan pi on n. And that is what we were being asked to show, so that's as required. Alright, so that's it for part 1. Now for part 2, we were told hence, so we're given that word hence, which means usually, in most cases, use what you just showed. We want to evaluate the limit as n goes to infinity of n tan pi on n, and we have to obviously give reasons for that. Now notice we've got a tan pi on n and we have a tan pi on n in what we just showed. The only difference is where we had an r squared, now we've got an n. So I guess there's a bit of work to do, but as we'll see, it's not a huge amount. And I think the starting point of the logic is to note that if we've got a regular n-sided polygon kind of sitting outside a circle, as n gets bigger and bigger and bigger, the length of these lines will get smaller and smaller and smaller. And as n goes to infinity, essentially the length of these lines will just become just a single dot. And essentially together they'll all literally form the circle. They'll just be the dots that connect to make a circle. So what we can say is that as n goes to infinity, I guess we could say it as the regular n-sided polygon will I'll say will converge to a circle. And so it's worth noting that the area of the whole polygon, the area of an n-sided polygon would be equal to, if we think about this one triangle, we'll have n of those triangles because we'll have n sides sitting outside the circle that can all form their own triangles. And so if we've got the area of one of those triangles being what we just showed, the area of all of them would simply be n times that. So it would be n times r squared times tan pi on n. So therefore what we can conclude is that since the n-sided polygon is going to converge to a circle, then its area will converge to the area of a circle. So what we can say is that the limit as n goes to infinity of this area, n r squared tan pi on n, that will simply go to the area of a circle, which if our radius is r, that's just going to be pi r squared. Now, given our limit is in n, that means r squared is essentially just a constant, so we can bring it out. So we can say r squared times the limit as n goes to infinity of n tan pi on n is equal to pi r squared. And so these r squareds cancel, and so therefore we can conclude that the limit as n goes to infinity of n tan pi on n is equal to pi. And that is the limit that we were interested in, n tan pi on n, n tan pi on n. So it just converges to pi. So that's how you do part 2. So as you can see, it's not a huge amount of working. You just need to make that logical leap to notice that this polygon, as n gets bigger and bigger, you get closer and closer to it just becoming the circle. And actually, I've had a student quite a while ago now send through a question that essentially asked us to prove this exact same result, albeit it was slightly different. It was in the context of complex numbers and slightly different format of the area, because we ended up with sine and cos instead of just tan, but it's ultimately the same result, and we wanted to show this exact same limit. So I might actually give a link to that, because again, if this type of question is new to you, it might be worth getting another look at it in a slightly different context, because this kind of result is a good one to be familiar with, so that when you get questions like this, you kind of almost know what you're working towards, and then it's just a matter of, you know, jumping through whatever hoops you've been asked to jump through to show it. So yeah, that's it for that question. Hopefully that's all made sense, and you've been able to follow along with all of that. If this was a question that you struggled with, that I guess you didn't really know where to get started, I guess the key for this was to kind of, I guess, make the link that this one triangle can be broken up into two, and once you realize they're congruent, things kind of fall out from there. So hopefully now that you've at least seen it once, it's something that you'd be well placed to have a good crack at if you encountered this on an exam. All right, tick boom.